let's review some notation for sets and for tuples. If we jump to the glossary and look at sets, we start down here with names of some special sets and tuples. The empty set is the set that has no elements in it. The empty string, lambda, is a string with no characters. That's a tuple, a sequence of n is the natural numbers starting from 0, 1, 2, 3, etc. And that's a set. There's really no order and no duplicates in any set. We go big theta, we'll talk about that later on. Power set is one of the set operations that takes a set and generates a set of all sets. Q is the rationals, R is the real numbers. We can put R plus and make the positive real numbers, or R greater than or equal to 0, make all of the non-negative real numbers. And then Z is the integers, and we can do the same things. So Z is all of the integers, both positive and negative. And so everything like -3, -2, -1, 0, 1, and we get the idea. Those are the names of some special sets. And now if we do look at some set operations, actually the best way to do this is probably by just clicking that and going over to table 5.1, where we see the key definition for sets is the element of. We use lowercase letters for elements, uppercase letters for sets, and this is just true or false depending on whether element A is in set capital A or not. The number of elements in A is just the vertical bars, like absolute value, and this number may be infinite for many sets, like the set of all natural numbers or integers or reals. A is a subset of B, and I'll often put an underline because we'll still consider a subset even if the two sets are the same. A is a subset of B means everything in A is also in B. If it's in A, then it must be in B. And we just define this in terms of the element of and some logic. So all of these other things are just going to come from logic. A equal B if the two sets have exactly the same elements. The complement is like the negation. Sets are always drawn from some universe, and so this is everything that's not in A. We have the union, which is like the OR, and it's defined, in fact, in terms of OR. Elements are in the union if it's in either A or B, or possibly both. The intersection is defined with and so elements are in A intersect B if it's in both, and otherwise not. Continuing down in this table, we get the more exotic ones. Set difference, which is subtraction. From A, take out anything that's in B. We get the symmetric difference, which is if something is in one or the other of A and B, but not in both. And there's disjoint union, which insists that the union, there can be nothing that's in both, otherwise it gives an error. A very common one, and not exotic anymore, is the one that we use to make tuples. This is the Cartesian product. And what this does is it takes two sets, takes every element, little a in set A, every B in set B, and makes the pair A comma B, and does this for all ways of taking an A and a B and makes a set of those. So we start out with single elements in each set, and we get pairs. And we can continue to, those single elements may have started as pairs, and you get triples and quadruples as well. So, power set starts with a set and gives back a set of sets. family of sets, all of the possible subsets. And some people use the to the a notation because that's the number that you're going to get. So the size of the power set is the exponent 2 with the exponent of the size of the set. And then there's also, you can take collections, you can choose elements out of a set, and we'll get back to that one later.